Okay, so welcome back to the fourth lecture of particle physics and the standard model. So let me quickly recapitulate what we have done so far. We understood what a particle was, we motivated the field of particle physics itself, and then we found that symmetry is a very powerful guiding principle for discovering newer fundamental concepts in high energy physics, right. And we saw that there is a neat application of symmetry that persists in the flavor sector, where you can write down baryon octets, meson octets and so on, and make predictions of mass spectra of these composites. And we also saw how symmetry plays an intimate role in our day-to-day life in the natural world, because we are made up of stable particles, we interact with stable particles, and the stability of every particle species is ensured by some symmetry or the other, right, via Noether's theorem in most cases. Today we will explore further aspects of symmetry, and let me give you a rough module on how the rest of our exploration of symmetry goes. Okay. So let me write that down. So here is a little sketch of where we are going. So we will be dealing with two kinds of symmetries that we see in nature. There are many ways to classify them, but this is one useful way. Okay, we will do discrete symmetries. What do you mean by discrete symmetries? Operations like parity, charge conjugation, time reversal, some combinations of these, and we will see what it means to put all of them together. Okay, CPT. And obviously the complement is continuous symmetries, which can be further classified into internal continuous symmetries. What do I mean by that? Things like spin, global charge, isospin, and so on. Okay. Now the word internal would make more sense if I write down the other one. The other kind of symmetry, continuous symmetries, we will be dealing with are space-time symmetries, right. For instance, rotations, Lorentz transformations, and so on. Transformations of coordinates that leave your theory invariant. That is the symmetry here. Okay. So that would mean that internal symmetries are when you do not make operations on space-time coordinates, there are some operations internally on the fields themselves, for instance, okay, that leaves your theory invariant. So that is our remit. Okay. Alright, so let us just jump right into it then. Let us start with P, parity. Alright. So I am sure you all know what parity is, right. Simply put, it's the operation of parity is mirror reflection, right. But more precisely, what we mean by parity is inversion around the origin, right. It's not a plane mirror that we are talking about particularly. Okay. So formally by parity we mean reflection around a point mirror, for convenience you put it at the origin, so that you take x to minus x, y to minus y, and so on, right. Okay. So let us see if we already know a few things about the operation of parity, and whether we already know certain interactions and theories that satisfy parity, that have parity as a good symmetry. Okay. So let us take electromagnetism. Would something change in electromagnetism if you flip the coordinates this way? Would electromagnetism still be the same if I flipped the coordinates? If yes, why? How do you know this? In a mirror, would we still have Ampere's law and Coulomb's law, Gauss's law, all the things that we love? Right, okay. So how do we see this? This is the warm up to the entire course actually. We're going to deal always with equations to see these things, okay? So what equation should I write down to see this? Yeah, Maxwell's equations, obviously, exactly. The equations of motion of electromagnetism, that should do for now, right? Okay, good. Magnetic field is a pseudo vector. We'll see all of this in action, okay? Let me write down, before I write down Maxwell's equations, let me write down something even simpler. Let me write down the Lorentz force, okay, and see how this goes. So, the Lorentz force, I'm probably not writing the spelling correctly here. Maybe, yeah, no, it is with a T. It is this Lorentz. Right? With both the electric and magnetic fields, correct? Okay. Now, under R going to minus R, what happens? What happens to the electric field? If I flip, it goes to the negative. Yeah, exactly. It goes to its own negative. Right? That's intuitive, right? You can take any test case of a static charge, for instance, right? The field lines just flip. And Pathsadi just mentioned, what happens to the magnetic field? Sorry? Yeah, exactly. It does not flip. Exactly. Right? And you can convince yourself of this by taking the Biot-Savart law, for instance, right? The current flips, but then the direction of the magnetic field doesn't flip. The current flips and the coordinate flips, but the magnetic field doesn't flip, right? Okay. Now, put together, I flipped the sign of E, I flipped the sign of B. Sorry, I have not flipped the sign of B. What happens to V? It goes to the minus of itself. So, the entire right hand side has flipped, which is just what we expect, right? And the force has also changed sign. Okay, so let me just write that down. The force has flipped sign, just as you expect, right? That means the acceleration has flipped sign, again as you expect, because you flipped the sign of the position. Okay, very good. Of course, let's see this quickly in action in Maxwell's equations, and for the IISc course this will be an assignment problem, okay? So, I am just going to write down the Maxwell's equations where we can actually see this in action in an equation of motion. Let me know if I am making a sign error. Yeah, I don't think I made a sign error. Okay, good. Now here, what happens to the grad when I under parity? Goes to the minus of itself, correct? Okay. So what happens to the electric field? It also goes to the minus of itself, so this doesn't flip. The first one is preserved, the first equation of motion. In the next one, again on the left hand side both terms flip sign, the magnetic field doesn't flip sign, right? Time also doesn't flip sign, right? We just flipped the spatial coordinates, we have not done anything to time. So the right hand side sign is preserved. In the third one, on the left hand side, the grad has flipped sign, the magnetic field hasn't, but that's okay because the right hand side is 0, so it's still fine, right. And finally in the last equation, magnetic field hasn't flipped sign, the grad has flipped sign, but on the right hand side both the current and the electric field flip sign under R. So we are good, right. So what we say now is that under electromagnetism, parity is a good symmetry. The world is the same in a point mirror as far as electromagnetism is concerned. Okay. What about gravity? Is gravity the same in a mirror, point mirror? If so, why? What is the equation? Think of the equation. Don't be blanked. Just think of the equation. Gauss's law. Okay. Think of a simpler equation. Yeah, Gauss's law. Sure. Gauss's law is a very generic thing actually. Doesn't have to be for just gravity or electromagnetism. Yeah, exactly. The potential, right? Is proportional to 1 by the modulus of R, the magnitude of R, right? So put differently, there is spherical symmetry baked into it, which we saw in the first lecture also, right? So again that tells you that gravity also respects parity. Okay, these are all different ways to say the same thing. Okay. Good. Now what about the strong force? What is your guess? We have not learned anything about the strong force so far, but what do you guess actually? What is a strong force? It is a sort of a binding force between quarks, between nucleons and so on, right? So I'll just tell you, the strong force also respects parity. Okay, and one of the quickest ways to see this is to inspect the potential. It's an effective potential. Okay, in other words, it's not really a fundamental equation that I'm writing down. This is what is seen to work. Okay, you can always write down a potential for any interaction at some distance scale. So the quark anti-quark potential is seen to look like this. Okay, there are actually we'll see when we get to Lagrangian formalisms, we'll see the deeper reason why strong interactions respect parity. But at this stage one can look at the potential and see that this is also made up of terms that go as the magnitude of R, and so flipping the coordinates doesn't change the sign of the potential. Okay, okay, good. All right, so let's inspect some more aspects of the operation of parity itself. All right, so let me open a new page. Okay, so we already had a glimpse at this when we operated parity on the electric field. It flipped sign. On the magnetic field it didn't flip sign, right? So obviously we can generalize this to all vectors, correct? Put differently, if I take P as the operator of the parity operation, if I denote it with the symbol P, and I operate parity on some vector, right? and if it flips sign under these, under the flip of coordinates, what is this called? What is such a vector called? It has a few names. You must have heard of it. No, it's a polar vector. This is a polar vector, right? Some people call it a real vector, and in particle physics context we just say vector. Okay. So conversely, wait, before we get there, so can you name some polar vectors? We just saw one. Yeah, we just saw one, electric field. Yeah, exactly. Position itself and derivatives of it, right? And time derivatives. Good. Force, as we just saw, right? And so on. Okay, good. Okay, so from here, there is a way to see that the existence of the other vector, right, which doesn't flip sign, is inevitable. How? Because imagine I had two vectors, two real vectors, okay, alpha and beta. I can always construct a cross product, right? And then if I apply parity on this, both alpha and beta flip sign, so obviously the cross product is not going to flip sign, right? So that says that the existence of polar vector implies the existence of, what is this called? Axial vector, right? Also called, what is the alternative name for this? Yeah, pseudo vector. Doesn't act like a real vector because under coordinate flip it doesn't do anything. Okay, good. Good, I am sure you have encountered all this before, but it is good to refresh your memory on this, okay, for what is coming up. So examples. Good, torque, because you know that can be expressed after all as a cross product of real vectors. Angular momentum, good, right? The magnetic field, which we just wrote down, you know, in the Biot-Savart law this also goes like this, right? A cross product. So generally you can always express, there is always a way to express pseudo vectors as cross products of real vectors, okay? Okay, good. Now okay, so here is a quick sanity check. When we wrote down the Lorentz force, right, where did we write it? So here, so when we wrote down the Lorentz force here, on the right hand side we wrote down two polar vectors, right, and then they flipped sign. On the left hand side we wrote something which is a force, and thankfully it also flipped sign. It is a polar, because we know separately from the Lorentz force that the force should be a polar vector, and it also flipped sign. So that is a good sanity check, right, that electromagnetism indeed does respect parity, correct. Now with that in mind, let me ask a question, okay. Suppose I had alpha as a polar vector, okay, polar, and some gamma as an axial vector, alright. Can I ever have a force that is a combination of these two? Is this possible? Can I ever write it down this way? So alpha flip sign, right? Let's do this. Let's apply parity to this, right? On the left hand side, I know that force, independent of how whatever it is, it's a polar vector. So I've flipped sign, right? Force is proportional to acceleration, so it has to flip sign. Alpha has flipped sign, but gamma hasn't flipped sign. So what has happened? Is this even possible? Is it legitimate? Okay, good. So, okay, this is where we are getting into the real weeds of the course, okay? It's perfectly legitimate, because who told you that the world has to look the same in a mirror, right? We saw 3 cases. We saw that for electromagnetism, the world looked the same. For gravity, the world looked the same. For the strong force, the world looked the same in a point mirror. But that doesn't have to hold all the time, right? So you don't have to demand that all the equations work out in a mirror. Actually, it depends entirely on the interactions themselves. Okay, so this is perfectly legitimate. It just means that this is not really the force is still there. The force is just looking different in a mirror. That's it. Okay, it's psychologically very troublesome that the world can look different in a mirror, but it's completely allowed by the laws of physics. Okay, this did cause a lot of psychological problems. It still causes a lot of psychological problems to physicists, and they're trying to fix it with various field theories and so on. But it's perfectly possible. Okay, and in the rest of this course, we will see many different levels of this concept of why it is perfectly possible, why it makes sense, where it doesn't make sense, what are the consequences of this, and so on. Okay, violations of deeply cherished symmetries is where all the magic is. Okay. So what force am I talking about here? Do we know a force, a fundamental force that doesn't respect parity? The weak force. Exactly. The weak force, not good under parity. Okay. Okay. In a sense, it is a combination of polar and axial vectors. We will see the meaning of this very precisely as we get into the field theory aspects of this. But the reason the weak force by and large does not respect parity, in fact it violates parity in a very maximal way, and that's because it's a combination of polar and axial vectors. Okay. So it vanishes like a mirror, in fact. It vanishes like a vampire in a mirror. Completely vanishes in a mirror. Okay. Okay, very good. So let's look at the history of the discovery of this violation of parity in the weak force. Why are we going into history? Because it's very instructive. Okay, we will learn a lot of good physics from this. Okay, so history of discovery has to do with something called the tau theta puzzle. Okay, it was found as long back as 1949. Okay, so what is the tau theta puzzle? So back then, physicists had discovered a couple of mesons. Mesons are quark antiquark combinations, right? So they discovered a couple of mesons. They called the tau and the theta. Okay, and these mesons contained the strange quark as it was discovered later. Okay, that's not terribly important. The thing about these mesons was that they both had a nearly identical mass as far as all the experiments within their precision went. They had the same mass, okay, they had the same spin obviously, well not obviously, so they both had spin 0 and they had the same electric charge, okay. But what distinguished them as two separate entities was that the theta meson was seen to decay exclusively to charged pion and a neutral pion. What are pions? They are made up of what? U and D quarks basically, okay. So the charged pion is made up of UD bar, this one is U bar D, and the neutral pion is actually, if I write it as a quantum state, it's actually a superposition of UU bar and DD bar, okay. Okay. So the theta was seen to go to pi plus pi 0, and the tau meson was seen to go to exclusively to 3 pions, okay. So if they have two exclusive fingerprints like these, then they are different particles, alright. So now it was known already that the pion, okay, carried an intrinsic parity of -1 actually, okay. And that meant, and parity is a quantum number that you multiply, so that meant that the intrinsic parity of the theta was 1 because it's -1 times -1, and the intrinsic parity of the tau was -1 because it's -1 times -1 times -1 on the right hand side, right. So this is like any other quantum number that you assign to a particle, right, like spin and charge and so on. So this is another intrinsic quantum number that you assign, and that is how they knew that since the tau and the theta they go to different final states and then they have completely different intrinsic parities, so they assigned completely different identities to these two mesons, right. Okay, so there was a little sleight of hand here. I just told you something about intrinsic parity. I didn't tell you exactly what intrinsic parity is, right. So that's what we're going to do now and then come back to the tau theta puzzle, alright. So what is intrinsic parity? So I told you that it is a quantum number like any other quantum number, right. So what does it precisely mean? So it means that if I treated particles as a quantum state, right, I can operate upon it with the parity operator, and if it's an eigenstate of this operator, then I should get eigenvalues of plus or minus 1. How do I know that? Because I do know that if I apply parity twice, I should get back the same state. That much we know, right. That is inviolate at least, right. So I know that the eigenvalues have to be plus or minus 1, right. I did another sleight of hand here. I talked about this a little bit in the first class. We talked about how particles are excitations of the quantum field in a particular space, Fock space. This is a restating, what I have done here is restated that statement. What I am saying here is that particles at the end of the day have to be treated as quantum states, okay, not on Hilbert space, on Fock space, but for now think of it as just Hilbert space right now, okay. So that's why any particle I can write as a ket like this. Good, very good. Okay, so in other words, P square is nothing but the identity, and maybe later we will see that the operator P can be represented in matrix form and so on, okay. If we have time we will get into all that, but for now just think of these as abstract operators, okay. Alright. So this tells me that I can have either real vector states or pseudo vector states, right? Vector particles, pseudo vector particles. Intrinsically they are vectors and pseudo vectors because of this. And so let us see how much we are getting into this. Okay, good. So okay, now that I have introduced the concept of vector and pseudo vector, maybe we should also talk about scalar and pseudo scalar states, right, which should be trivial at this point, right. So we already saw under what a vector is. If you flip sign, if you flip the sign of the coordinates, the vector also flips sign. So what is a scalar then, a real scalar? It should not flip sign, exactly. A real scalar would be something that if you flip the coordinates it doesn't. What is a pseudo scalar then? Yeah, it should flip sign, exactly. Very good. Okay. So that brings us to scalar and pseudo scalar states. Okay, very good. Okay, so now let's think a little bit more about the intrinsic parities of various species. Okay, I just told you that the pion has an intrinsic parity of -1. So I just pulled it out of nowhere, right? I basically stated the pion as a pseudo scalar. So let's think a little bit more about where the intrinsic parities come from. Okay, so from the physics that you already know, okay, what is the intrinsic parity of a photon? Do you think it's +1 or -1? No. How can it be? We just saw that it cannot be 0. We just saw that the eigenstates are, the eigenvalues are either +1 or -1. +1. So what is your reasoning behind +1? Yes. It will still be a photon, but why can't it be a minus photon? It's not.
Because photon rises from electromagnetic interaction producing that electromagnetic interaction.
Yes. So the photon, so the interaction itself maintains parity, but what about the states taking part in that interaction? That can flip sign. Okay, this is a little tricky. It turns out that the intrinsic parity that you assign to the photon state actually, right, not the interaction, the state, it is -1 actually. Okay, and how do you see this? Because the photon actually appears, you will see that the photon appears as the vector potential. Remember the vector potential when you wrote down Maxwell's equations? You could have rewritten them in terms of a scalar potential and a 3 vector potential, right? Correct? And just for completeness, let me just write it down. A0 is phi, right? You had these, right? And you know that the electric field flips sign. So you can see this already. So A flips sign, and both the components of A flip sign. The magnetic field doesn't flip sign, and the 3 vector part has to flip sign because the grad flips, right? So this is one way of seeing that the intrinsic parity of the photon is the photon field basically, which you represent as a photon state. It is -1. Okay. Now next, if you were to write the intrinsic parity of a quark. This is much harder to tell, okay. I am just going to tell you the answer. It is +1 and this assignment is completely arbitrary. Okay, there is no underlying physics to fix this. So, in the same breath I am going to say that the intrinsic parity of an anti-quark is -1, okay, because what we can actually fix is the combination of a quark anti-quark, or for that matter the combination of a fermion anti-fermion pair, okay. This is how we generally write FF bar, that is -1. And why is that -1? That's much harder, that's very hard to actually explain in the course. We can probably take it up in some tutorial session or something, but for why this comes about, I would point you to Srednicki's QFT book, probably is also in Matt Schwartz's book, but I think Srednicki explains it in good detail. Go look at this, the 40th chapter, equation 40.17, for why a fermion antifermion pair has an intrinsic parity of -1. Okay, and here already I am using the fact that parity is a multiplicative quantum number, which should be intuitive by now, right. We are acting on states, so if I have a combination of states, then the eigenvalue is the product of the intrinsic parities, right. Okay, so that's for these fermions. So the intrinsic parity of an electron I would take as 1, intrinsic parity of a positron I would take as -1, going by the same convention, right. Now here is a trick question, and after this I will try to wrap up soon, okay. What is the intrinsic parity of a neutrino? I do not expect you to know the answer to this actually. It's a very trick question. Okay, so the trick is that we cannot do this, okay. There is no intrinsic parity for a neutrino. Why? Because the neutrino, right, it's not an eigenstate of parity, okay. Why is that? We will see that all neutrinos are left-handed. There is a very certain sense in which that comes about. Left-handed meaning it has, they have left helicity, so to speak. It's not quite helicity, but you are familiar with helicity, right? I am sure you are familiar with helicity, how the screw turns around, right? So neutrinos, their spin and their momenta are always aligned in a certain way, so that if you flip it in a mirror, right, a screw flipped in a mirror looks different, right? So if you flip it in a mirror, a neutrino helicity, so to speak, the actual word is chirality, the helicity would also flip in a mirror, so that means it's not an eigenstate, a parity eigenstate, okay. So I am going to put the subscript L to denote that neutrino is left-handed. If I act parity on it, I get a right-handed neutrino, so it is not a parity eigenstate, okay. So I cannot talk about an intrinsic parity for a neutrino, okay. I am slightly jumping ahead here, but just to give you an idea of what some of these exceptions are. This is where all the fun is, okay. So we will see this all in more detail as we get along, okay. And finally, the parity of a 2-particle state with orbital angular momentum L, okay, that turns out to be -1 power L, okay. And this is something that you can see for instance, in the case of a hydrogen atom in your quantum mechanics, the case of the hydrogen atom, go look at the spherical harmonics and you can convince yourself. If you take, an electron and a proton, for instance, look at the wave function, you can convince yourself of this, okay? And I'll probably give this as an assignment problem also, okay? Okay, so with this in mind, with all this in mind, we can now finally write down the intrinsic parity of a meson. That would be, I'll just give the answer, it's minus 1 power L plus 1. Why is that? Because this part comes from the angular momentum stuff. Okay, I should probably have said meson has an intrinsic angular momentum with angular momentum L. So this part comes from the angular momentum, but a meson is also a fermion antifermion pair, right? So that's a minus 1. So a meson bound state overall has minus 1 power L plus 1. Okay, so this is how we were able to assign for the pion, which was known to have 0 angular momentum. For pions, the parity is minus 1. Okay, so this is what lies behind the theta tau puzzle. So I'll wrap up here, and in the next lecture we'll see how we can apply these to understand that parity is maximally violated. In the weak interactions we'll look at Wu's experiment and probably we'll get to charge conjugation as well. Okay, thank you.